Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is the second in the series on motion with a variable force. Can I again remind you that if the force is variable, the acceleration too will be variable, and so it's not appropriate to use the Suvat equations. The Suvat equations should only be applied when the acceleration is constant. So let's again look at the general situation. We're looking at a particle moving in a straight line, and we want to consider cases where the particle is subject to resultant force that's not constant. So there's our customary setup. You've seen that diagram before. We need to consider in each case how f varies. It could be that f varies as dependent on time. It could be that f varies on the basis of displacement. It could be that f varies on velocity. And the fact that the middle one is in red is the cue that this is all about force depending on displacement. So let's look at a particular problem. We've got a particle of mass 0.5 kilograms. It's again on a smooth horizontal surface, so there's no friction. It has an initial velocity 2 meters per second in the direction of a point A. After t seconds, its displacement will be x meters, and it will be moving with the velocity v meters per second, where the direction OA is taken as the positive one. Now, force of 0.1 x newtons acts on P in the direction AO, so it's a restraining force. You might like to think of that in the same terms as, say, a spring. You pull a spring, the spring tends to restrain the motion. So we're interested in the velocity when the particle has a displacement of 3 meters. Well, there's a diagram which simply summarizes the information in the question. I could add to that, I suppose, that the mass is 0.5 kilograms. The initial and the general velocity is shown, and the relationship to displacement. There's the force diagram. Notice, because it's a restraining force, because it's in the opposite direction to the particle's motion, and the particle's motion we're taking as defining the positive direction, we've got the force arrow and the acceleration arrow in the opposite sense. So that will lead us to an equation, but first let's just remind ourselves of the question. When x is 3, we want to know what v is. So we can anticipate that that will be giving us an equation in terms of 0.1x and a. So our equation is going to look like that. It's just f equals ma. So we've got f on the left equals ma on the right, and the minus sign accounts for the fact that it's a restraining force. Now, this equation looks deceptively like the sort of thing we had in the last video, but the big difference is we have an x on the left, whereas before we had a function involving t. Now, this means to say that although it looks very clever to replace the acceleration by dv by dt, so that we can think in terms of a variable acceleration, having dv by dt is next to useless, because we can't integrate with respect to t if x is a function of t and we don't know what x is. Now, this is where there is a really sly maneuver. If we take dv by dt as the current form of acceleration, we can think of v as being a function of x, in which case we would naturally get dv by dx as our derivative, and to relate the two we'd need to multiply that by dx by dt, so that by the chain rule the right hand side is again dv by dt. Now, notice on the right hand side that second factor, that's what we'll recognize as just v. So we can write that right hand side as v dv by dx. Now, that's the sly maneuver. Instead of writing dv by dt for the acceleration in this case, we write v dv by dx, and that's eliminated t altogether. So our first thing to do then is to take our equation, which was in this form, and rewrite it with dv by dt changed to dv by dx. Well, an obvious simplification is to multiply by 2, so that we get v dv by dx is equal to minus 0.2 times x. And then if we separate the variables, we'll get the integral of v dv by dx dv is equal to minus 0.2 times the integral of x dx. So from that simple integration, v squared over 2 is equal to, well, it will be x squared over 2, so if I make it minus 0.1, then we'll have x squared and plus c. So v squared over 2 is equal to minus 0.1 x squared plus c. Well, we have our initial conditions. When x is equal to 0, from that diagram above, that recalls that v is 2. That's when it starts. So we can substitute and get on the left 2 squared over 2 is minus 0.1 times 0 plus c. So c is equal to 2. So that gives us then that v squared over 2 is equal to minus 0.1 x squared plus 2. Well, that looks terribly untidy with that v squared over 2, so let's make it v squared is minus 0.2 x squared plus 4, and then finally, to tidy up the signs on the right hand side, 4 minus 0.2 x squared. So that simple process of integration using that slime maneuver of using v dv by dx, it gives us an answer which we can now use. So we move to the next stage. That's where we've got to. So if we're interested in the value of v when we substitute x equals 3, we're going to get 4 minus 0.2 times 9, which is 4 minus 1.8, so the square root of 2.2. So if we work out the square root of 2.2, we get, using a calculator, approximately 1.483, etc., which gives us 1.483 significant figures. So that enables us to answer the question. There we are, the velocity is 1.48 meters per second when the displacement is 3 meters. Well, that's what the question asked. But let's just think a bit further about where this could go to. We started with the equation v dv by dx is equal to minus 0.2x, and we integrated it to get the, the first step was to separate the variables, expressing it in that integral form, and that's what I used to work out. But you could also do it by definite integrals, because if we say let the value of velocity that we're interested in be v0, v0 is just a value, then it will be the upper limit of an integral which starts with 2. So because v changes over time from 2 to v0, and while it's doing that, x is going from 0 to 3. So that will give you an equation, just as it will give you the same value that I got before, but a slightly different way of looking at it. So you can use a definite integral in this sort of situation. On the other hand, if we keep to the idea of using an indefinite integral, which led us, once we worked out the constant, to the expression v squared is minus 0.2 x squared plus 4, then we could use the fact that v is dx by dt to push the calculations one stage further. So thinking in terms of v as the square root of that right hand side, from this expression as we had before, we would get dx by dt is equal to the square root of 4 minus 0.2 x squared, just as before, but we've expressed the v as dx by dt. Now that will again separate, so that on the right hand side you'll have the integral of dt, and on the left you'll have the integral of 1 over the square root of 4 minus 0.2 x squared dx. And you should recognize that right hand side as the kind of integral that yields itself to the standard form for the inverse sine of x, or if you prefer, the inverse cosine of x. So that brings us to the end of this particular video, where we've looked at the force being defined in terms of displacement. The next one in the series will be the first of two, which look at force defined as a function of velocity.